Hi everyone, we are DeepFloyd team. We will tell you about large language modeling for text-to-image models and about DeepFloyd new text-to-image diffusion model that will be open source very soon, and we're happy to say it's a new state-of-the-art model for text-to-image. And first of all, I want to tell about our team. We're working as a research lab as a part of Stability AI. Here, Daria, she is a senior researcher, and Alex is one of the main guys who behind if model. Also me, team lead of Deployed Lab, and Ksenia, our data scientist. So first of all, we are talking about large language models, but they are language models. So why should we talk about them in context of text to image? So the question is very interesting because nowadays everyone know about DALL-E 2 and especially about Stable Diffusion, the most popular text to image model ever, one of the greatest things that we have in the open source. And I don't want to spend time about telling you what is it, but it's a diffusion model that can convert the text to the image in several seconds on almost any PC and laptops and maybe mobile phone. So it's very popular nowadays, and one of the things that people maybe not talk a lot about, it's that it consists of the several parts, and the language model inside is a huge part of the Stable Diffusion model. So I will tell you briefly about DALL-E 2. It's one of the first popular text-to-image model that blow the people mind. And it can generate almost anything, not just avocado armchair, but maybe some complex scenes. For example, dog playing the trumpet in a jazz band, etc. So if you see the paper and you look at the images, you see, okay, this is a huge scheme that describes how DALL-E 2 works, but it starts from the text, a Corby playing a trumpet. So this text is converted to some embedding space using text encoder, and the text encoder is the language model that we are talking about now. And this is a frozen language model that are not trained during the DALL-E 2 training phase. I mean that this is text clip tower that have been trained before trained DALL-E 2, and it can convert this text to some embedding space. And after that, DALL-E 2 approach use the prior to move this vector to the image embedding space, and after that, unclip it to the low resolution pixel space. So, Stable Diffusion, this network that have been done by Robin and his team as a part of Stability AI, is a very popular network nowadays. And it also, it's a very complex scheme, maybe not the best one, but you can see this is the frozen clip part here too. What does it mean? It means that as same as DALL-E 2 have the frozen text encoder, Stable Diffusion is also have the frozen text encoder, but it doesn't make this kind of mapping from language embedding space to image embedding space, but it still have this frozen text encoder. And this information comes from text to embedding space. And after that, this information fuse through cross attention to the UNet, and there the magic begins. So the diffusion in the latent space and then decoding backward to the pixel space. The interesting part here that this is frozen clip model without prior that converts or map the text embedding to image embedding. So this idea initially comes from Imagen, the network we will tell you now.
It's obvious that there are some pros in using clip as a text encoder, because clip was training using text-image pairs, and obviously it contains some visual features inside its text embeddings. But there are also some cons with this approach, because actually parallel text image corpora, they're not so big as, for example, corpora on which large language models are trained on. So there is another idea with the model called Imagen. They take T5XXL language model. It's a great, huge language model, which was trained on a great amount of data on C4 corpus. And they use it as a text encoder. And it's frozen. So no weights are changing through the training process of Imagen itself. Actually, Imagen is our main source of inspiration. And I guess it's worth mentioning that Imagen works in pixel space, unlike Stable Diffusion, which works in latent space. And so our model, thus it works in pixel space as well. T5 is a large language model which is trained with the span corruption objective. Basically, it's encoder, decoder, transformer model. As you can see on the right, it's written that it was trained on C4 corpus. And the model itself, like the biggest model, XXL, has 11 billion parameters. And actually, this is the very language model which we use as a text encoder. Now we are approaching to our model, to DeepFloyd if model. And we just want to start with the results, actually, with some examples of our trained model, which can demonstrate that the language understanding of our model is really pretty good. As we all know, Stable Diffusion doesn't generate text well. It makes many mistakes, and it's really hard to get the desired image if you have like some sophisticated, complex prompt. But here you can see that with the T5 XXL as a text encoder, you can really get what you want in many cases, even if your prompt is pretty much complex. And here we also can observe that it has a basic knowledge of cardinality. So through the prompt, we can set how many objects we'd like to generate. And it works fine with some amount of objects, actually up to 5. So it really understands that if you have a prompt, 4 bottles of wine next to each other, it can really generate these 4 bottles. And moreover, it doesn't duplicate or clone objects. It makes some variations in the objects so they look more realistic. The last image, I think, is the most comprehensive and complicated one, where we can see like 3 objects, and in prompt we describe the particular space relationship between this object as well as their color and their texture.
As I mentioned, we deployed team, and we when we began to do this new model, we thought about that we are living in the age of not one neural network, but several neural networks that are combined with each other. So this approach, comes from different type of architecture and design. For example, modular synthesizers give you opportunity to not buy the final synthesizer of your dream, but you can buy different parts and construct the synthesizer of your, the best synthesizer you want, what fit your needs. And also you can construct your home, your ideal, room, or even buildings, yeah. And we thought, okay, we can construct this kind of architecture like Imagen, but also we can separate our parts and use, for example, first two stages, but not use the third one, for example, as a super resolution stage. I will tell you in the second several slides. But I think this is the core idea of our lab, to construct a lot of neural networks that are not like separate own things, but they come with the model approach, and you can combine them and see what happened next. And I hope in several weeks we will share you some additional idea that comes from model approach. In our case, we use several stages. First of them is made by Google. It's T5 frozen language model. It's a function. It takes the text prompt and return the embeddings, depending on how many tokens you use. In our case, we use 77 tokens, and we have 4096 dimension space. And after that, that textual information came to UNet, and our first stage model return you image in 64 by 64 resolution. In future, we will tell you that in reality, you choose any resolution you want, but this is the default resolution we use for training. And after that, we have different super resolution phases, and this image, it looks like amplification of audio signal, but in reality, we just increase the resolution of the image. And in the several two upscaler cascades, we came from 64 by 64 to 124 resolution. In our approach, we can use this model in separate, but the ideal pipeline for inference is to use them all together. So the difference between our model, its ImageGen, is in devil in the details. So in our case, we're using additional type of low and upper resolution blocks in first, second, and third stage model with a lot of additional cross-attention blocks to increase the text information that fuse from text model to the final image. So if you're interested, the use attention on the low resolution blocks, every skip connection blocks with cross and self attention, and we call this approach optimal UNet because it's we thought it's more optimal to use this kind of cross attention per block approach, and it gives more gain. So about training data, we use open source. We love open source, so we use Line 5B dataset, but it's not only English dataset. It consists of many languages. And Christoph from Line made a huge work to create Line 2B dataset. And also his team and himself made a large work, he and especially Rome. Thank you, Christoph and Rome, for doing that. Made several things to do this dataset better for users. And they make aesthetic scores. So it's basically clip score that have been trained based on human evaluation and human markups that show how beautiful data is. So, for example, you can see that this low aesthetic score returns very unpleasant images, but if you increase this aesthetic score, you will see that maybe more pleasant, more stock-like image comes to this threshold, and in the end of the day, you will come with very beautiful, or maybe not, depend on your taste, images. So we made a decision to threshold aesthetics by 4.5, and it allow us to use 1.2 billion images. And after that, we found another strange behavior on Stable Diffusion. And this is one of the example you can generate by typing value 002. And this is very strange image that came almost every time with a lot of artifacts and a lot of noises, but the same yellow chair and these paintings of the wall, we thought why it happened. And after several hours of research, they understood what almost 0.1% of the dataset are consist of the one similar images, because this dataset haven't been deduct or deduplicated as need. We also made a lot of analysis how much data set we have been deduct, and I will tell you this is a lot of data. It's almost 25% of data have some duplications. And also, I don't want to like give you a lot of textual examples, but as you can see, the most popular textual description of the image that have been deducted is value 2. So because of that, Stable Diffusion have been overfit on this image, and the behavior was very, very strange. Okay. Also, it's very interesting that even on the text, on the image collision type, we have this type of behavior known as the zip flow, but it's usual, as we know. So this is a very popular case that we have been deleted from dataset, and you can see that Stable Diffusion can generate it precisely because it's overfit on it. But in the case there you have like almost 0.1% of the same images. I mean, in every batch you train, you have some images of the same yellow chair. It allow model to not just remember it by heart, but also to hallucinate it in very strange manner because of this damage the ways of the model. We don't want to. This stuff, almost more than half images from Stable Diffusion have this strange behavior. I want to tell you about how to train and decide which thing you should use or not use during the train these kind of big image models. So on the early days of doing if model, we made several experiments. They took from 10 hours to maybe a day and a half. And after finishing them, we want to decide which model are better. But we didn't saw the good results on FID because there was a big stochasticity in FID score, clip score, and these training. But we saw that on the train loss, you cannot decide which model is better. You have just noisy, almost plain line with no information at all. It maybe looks a little bit noisier in the end, so it's give you no information. So we made a decision to do static steps. For example, if you have 1,000 discrete diffusion, so you can hold or decide to evaluate on these specific steps to avoid this stochasticity in the validation loss. And we using Bayesian biases to log this using just several lines and changes. We made a good approach that was very representable, as you can compare with previous stochastic loss that I have show you. You can see here that, for example, this model, the instance normalization, it works much better than without it by this loss, and it's very visible, and we understood, okay, let's do this kind of approach. So we have 3 stages of our model, and by using Bayesian biases, they saw how, not stages, so 3 sizes of first stage. I mean, first stage is the text to 64 by 64 model. And you can see that the smallest model is not as good as the largest two. So Bayesian biases give us opportunity to validate and see what happened. And when we have some spikes in losses, we can decide should we stop experiment or not. This was very, very representative, but without this idea of holding some discrete steps and validate them, we were blind. So this is a good idea maybe for future trainings to use this kind of steps. But this is cool to see what loss show us, but the main idea of evaluation and comparing the model is use mathematical metrics such as FID.
And we actually proud to announce that at least for now, our model has the best FID score on zero-shot COCO validation subset of 30,000 of images. We've actually conducted really many experiments deciding on the parameters, because once you generate image, there are several parameters you can choose from. It's a classifier-free guidance on the first stage. It's the level of augmentation, and also classifier-free guidance on the second stage. And you can imagine that we can't actually test the ultimate set of all these combinations, of all these parameters. And but through the random search, we've been trying to find the optimal set of parameters with which it's better to generate images. And after that, we've got this result. So on the left, you can see the table, which represents the FID scores of many text-to-image models. You can see, for instance, DALI 2, which we've already mentioned, and it has 10.39 zero-shot FID 30K. Also, you can see Imagen model here. It's 7.27, so it's like our parent ancestor. Yeah. FID score, the lower is the better, and we can see that our result is 6.66, and at least for now, it's the best result. Yes, and on the right side, you can observe several Pareto curves of FID score and CLIP score. FID score, it's the lower it is, the better. So it compares visual features of real images from the COCO dataset and the generated ones. And a CLIP score says how much the text description, the prompt, and the generated images are close to each other semantically. And it's the higher is the better. And so there are these Pareto curves of these two metrics, which allow us to understand how good are our generated images and how do they fit the prompts, the captions. And so we can see that we have really good results. So CLIP score, here we can observe our biggest and our best model, if 2.3 billion parameters. And so it has FID score 6.66 and CLIP score around 0.306 or 7. Yeah, so it's really a good result. During our evaluation, we've not only conducted quantitative evaluation, but we've also made a qualitative evaluation, meaning that we took some well-established benchmarks, for instance, party prompts, draw bench, and we generated images based on these prompts, and then we just evaluated by our own eyes. And we also actually hope to conduct human evaluation. But having only our own eyes, we discovered really interesting properties of our model. For instance, taken draw bench prompts, we've discovered that if we translate them into several languages, in this case we mean European languages, for instance German and French, and put these prompts to the model, it really it understands it. For instance, here you can see that if we take the prompt "a black-colored car" and translate it into German and French, the result of the model is consistent. So it really generated images fit the captions even in other languages. Because we use T5 as a text encoder, there were no non-Latin languages or non-European languages. Yes, but we definitely would like to dive into this property more, to evaluate it and to understand to which extent this property holds. Yes, and here, for instance, it's interesting to observe with some that in French language, the generated images, they look quite different comparing with the English, with the one generated with English prompt or with German prompt. Yes, because here we see sac à dos. It's a backpack in French, but in this French word, the part of this French word is the sac, is a bag. And we see that in French, the model understands it not so well. It's just pick this word sac as a bag and generates bag, not backpacks. Another great and very useful ability of our model is zero-shot image-to-image translation, which allows to make some alterations, some modifications of the initial image, to change its style or to add some details. For instance, here we have an image of some sketch we'd like to use, and would like to get it in the style of Minecraft. So what can we do with that? We can use like the forward diffusion process, whether we can infuse noise in our initial image in several steps, add, edit, and then we can stop at some point so that we see that it's not a complete noise. Yes, so we can see that some geometry of the image is preserved. And from this step, we can put our text prompt, for instance, Minecraft. We put it into our text encoder, our T5XXL, and then put it to the model, and thus reverse the process of diffusion with this text embedding. And here you see that we more and more we really get the image which fits our text description. At the same time, the final image really preserves the geometry of the initial image. So, for instance, we can use not only Minecraft, or we can put some other styles like zombie or origami or anime and so on. So with the knowledge of this large language model of T5XXL and the capabilities of diffusion models, we can really get this result. Also, we can change not only like the whole picture as we've just observed, but we can change and modify some parts of the image. So here, for example, we can have some special zones. Like here are the ears of this beautiful young woman, and we can change her ears, for instance, and it can be controlled with text prompts.
So I think that's all. This is deployed research lab from Stability. This is deployed Eve text-to-image model. I hope that the covers pretty everything from the train to the inference and the evaluation. And we will happy to see your feedbacks, and we really want you to try our model in the several time when it will be open source and everyone can try it.